muchas gracias por estar presentes el día de hoy. Tenemos con nosotros a la doctora Faeze Khademi. Ella trabaja para la empresa de trenes más grande de este continente, que es CN, y trabaja como ingeniera de puentes para la compañía de trenes central de Illinois. Ella tiene una maestría y un doctorado en ingeniería civil del Instituto de Tecnología de Illinois y es ingeniera civil graduada de la Universidad de Kashan en Irán. Entonces, en este momento salto al inglés para el resto de los invitados que tenemos en este momento y para que la doctora arranque con su presentación. Welcome everyone. That was Spanish. If it was maybe one of the few times you could hear, it is a very different language from English. I I think it's very different. Welcome everyone. Thank you for being with us this morning. This is the 23rd International Seminar Series at the Master's program in Civil Engineering at Javeriana University. We're welcoming all the professionals and students and all the professors that are joining us today to hear Dr. Faeze Khademi. She's a bridge rating engineer at the Illinois Central Railroad Company, and she's got a master's and a PhD in civil engineering, both from the Illinois Institute of Technology. She also has a bachelor's in civil engineering at the University of Kashan in Iran. And we are very happy and pleased and honored to have you this morning, Dr. Khademi. So please, the room is yours. I'll take care of questions and I'll take care of the attendees. So please go on.
Thank you, Federico, for the introduction. Good morning, everyone. My name is Faeze Khademi. Today, I am going to talk about a comprehensive study on design criteria, span types, and in-service maintenance of railway bridges. This session will introduce you to a basic understanding of how our bridge structures behave or respond. It is our hope that this understanding will help you identify the important components to pay special attention to during the course of your field inspection and what kind of information may be most critical. I'm going to start this presentation with a small background of myself. I got my master's and PhD from Illinois Institute of Technology. Actually, I met Federico first at Illinois Institute of Technology, and that's how we became friends. This picture to the left side is me on the day of PhD graduation. You see how happy I am to finally become a doctor. The picture to the right is me while working for CN Railway. So I started with CN Railway a couple of months before my graduation, my PhD graduation, on August of 2017, and I have been with CN since then. CN is the Canadian National Railway Company. It has so many routes all around US and Canada, so it's not working only in Canada. We have so many routes in US too. It has more than 20,000 miles network spans in both Canada and Mid-America to the south. It serves Canada and the Midwestern and Southern United States. And the important about the CN routes is that it connects all the three coasts, the Atlantic, the Pacific, and the Gulf of Mexico. As you see in this picture, this is the routes of CN, Canadian National Railway. And you see that it goes all the way from western of Canada to the eastern and all the way from north of US to the south of US. CN has so many groups and organizations. It's a really large company. We are with the Bridge and Structures group, and Bridge and Structures group is divided into 4 different groups: bridge rating, bridge quality, bridge testing, and bridge design. In the bridge quality, the inspectors will go to the bridge to inspect the bridges and see what kind of corrosions or other stuff they can take out from the bridge, and they're gonna give it to the bridge rating group. That's the same thing that bridge testing also does, but in their own way. The bridge testing technicians go to the bridge and test the bridge and give the result to the bridge rating group. In the rating group, we try to analyze the bridge based on those data and see if any repair or strengthening is needed for the bridge. If it's only the strengthening needed, then the bridge rating group is gonna propose those strengthening. But if it is needed to repair some of the parts or to replace the spans, then that's when it goes to the bridge design group, and our bridge design engineers will design those spans for us. The code that we are working with is ARIMA. ARIMA stands for the American Railway Engineering and Maintenance of Way Association. ARIMA comes in 4 volumes. Volume 1 is track, volume 2 is structures, volume 3 is infrastructure and passenger, and volume 4 is system management. What we work with in bridge and structures group is volume 2, structures. ARIMA is, you know that ASHTO is the code, the manual that is used for highway bridges. ARIMA is the manual which is used for railway bridges. ASHTO is the mandatory code. However, ARIMA is not mandatory, and you can use it the way you want it. So in the railway at CN, we use ARIMA for our analysis, for our design, for our testing, and for our inspection.
Ahí sí es en inglés, yo juraba que era en español.
ARIMA design manual is based on allowable stress design, ASD. It is for timber, concrete, and steel bridge designs. It is also for tunnel and culvert design. And it is for inspection, maintenance, and construction practices. There are different loads that are used in railway bridges: dead loads, live loads, and other loads. Dead loads are primary the span's own weights. Also, any other static load expect to remain for the lifetime of the span is assumed as dead load. Train or vehicular traffic are the live loads, temporarily in nature and usually in motion. The standard design live load for railway bridges is the Cooper E load. Cooper E80 is what we use right now for design of our bridges, and Cooper E50 is what we use for our analysis. And the way you convert E80 to E50 is simply by multiplying the load by 5/8. There are also other loads like impact, traction, and bracing, centrifugal, wind. Other loads are loads associated with the dynamic effect of the primary live loads or nature forces. The engineer analyzes the structure for a combination of loads and considers those which produce the maximum stresses. These loads, which may or may not be present at all times, are taken into account as they apply. Other loads include the following. The first one is the impact load. The dynamic load includes rolling and direct components that together can reach values at as high as 60% of the primary live load. Short spans will be subject to higher impact loads than longer spans. They're due to a combination of tracks and wheels geometry and suspension parameters of the lowering stocks. The condition of approaches will particularly affect the magnitude of the impact. We also have longitudinal loads. They occur in the direction of traffic during braking or acceleration applications of trains. Most affected are floor beams, towers, and bearings in the bridges. Another type of load that we have is the centrifugal force. Is a function of speed tilt, track superelevation, track eccentricity, and track curvature. They cause both vertical overturning and horizontal bending effect and are most pronouncing at high speeds. Another type of load is wind. Wind loads are applied to the structure indirectly on the train or directly on the exposed area of the structure. These loads have both overturning and horizontal effects and can become significant on long spans. We also have other type of loads like thermal, earth pressure, streaming flow, sidewalks, curb, railings. That all of them should be taken into account while designing and analyzing the bridges. The impact load in ARIMA is shown with this formula in the bottom that you see. This is the formula that is used when the speed is less than 60 miles per hour. But when the speed is larger than 60 miles per hour, this is the formula that we use for this impact load. This is also the code that we have for centrifugal force and longitudinal force in ARIMA. So I explained the longitudinal, centrifugal, and all the other loads. So I'm just showing you how they are presented in ARIMA manual. This is the seismic base acceleration in ARIMA. And this one is also the continuous of that one. In this table, you will see ARIMA, CV, and toughness of steels. So whenever you want to use different steels for analysis and design, you can use this table to see information about the type of the steel that you are using in your structure or superstructure, substructure. This table shows the ARIMA earth pressure. Whenever building and constructing the bridge, not only you must design the bridge and the span types, you also need to know about the type of the soil underneath the bridge. And that's when the earth pressure formulas comes into account. This is one of the CN bridges, the very simple one that you can see in the picture. Most of the CN bridges has this CN tag on them. For some of them, they might not put it there because it has been difficult, but we try to have the logo everywhere that we can. We have different span types, different bridge types. I'm gonna explain each of them for you. This one to the right is DPG, which stands for deck plate girder. As you see in the figure, it consists of two plate girder here, and the deck stands on the girder. So in other words, whenever the train wants to pass the bridge, it passes on top of the bridge. The TPG stands for through plate girder. It consists of two stringers, one floor beam, and two girders, as you see in the picture. And you see that the deck is placed in the middle of the two girders. And if the train wants to pass over the bridge, it goes through the two girders. Unlike the DPG that the train was go over the two girders, in TPG, the train goes between the two girders. This is the example of the timber span. This one is the through truss. The through truss is also whenever the train wants to pass over the through truss, it passes in between the two trusses. Although in the deck truss, as you see here, the train passes on top of the deck truss. And this is the example of the concrete bridge. We also have a couple of more bridge types, span types. Half DPG is simply we can define it as the DPG that the bridge is going in between the two girders. And the half TPG is the TPG span that the bridge goes over the two TPGs. And this is also the example of arch bridges in the bottom. You see that? So we have discussed deck plate girder, through plate girder, through trusses, and deck trusses. Each component of the bridge, depending on the type of span, is designed to perform one or more specific functions. The functions of the structural components in 4 component types of railway bridge spans will be presented on the next few slides. This is the deck plate girder or DPG. As I said, these are our two girders as you see in the picture, and the train goes over these two girders. The girder flanges are top, bottom, shelf angles, and cover plates and side plates, similar to beam spans with exceptions which has, in beam spans, we have multiple beams, shallower and rolled sections, but in the deck plate girder, we usually have only two large girders, as you see in this picture, to the left and right side. Primary components to resist bending moments. There is no redundancy of one of the flanges, which results in loss of the bridges. The top flange is usually in compression and bottom flange is usually in tension. Since bending moment is usually maximum near midspans, the role of these components are most important at that location. Rivet holes in the bottom flange near the midspans are vulnerable locations to fatigue crack initiations. The girder web primary component, the girder web is the primary component to resist shear. Since the maximum shear force is usually near the support, the integrity of the web is most important at that location. The stiffeners are bearing and intermediate components. As the name implies, these members help to stiffen the otherwise thin and very flexible girder webs. The bearing stiffener also has an added role of disturbing the end girder shear to the bearing support. And the lateral bracing, you see them here in the picture. We have both the top and bottom lateral bracing. These secondary members resist the indirect lateral and torsional forces such as wind and hunting of the train. This is the example of the deck plate girder. This is also another example. You see it from the top view. The primary member components of a deck plate girder spans are top and bottom flanges, shelf angles, components, webside plates, and cover plates. These are the deck plate girder from the inside view. You see the bracings. You see the stiffeners here. These are the stiffeners. This is the top flange, this is the bottom flange, and this is the web. This is another picture of the deck plate girder. Sorry, this one is the TPG span. So as I told you, the TPG span consists of stringers, floor beams, and girders. As you see in this picture, these are what is called stringers. So the load is first applied to the stringers, then it is transferred to the floor beams, and then the floor beams will transfer the load to the girders. Same as what I said for DPG spans, the web are taking the shear forces, and the middle part of the span is where the maximum bending is applied. We have different bracings for TPG spans, lateral bracings, knee bracings, and traction bracings. And traction bracings are those ones that resist the longitudinal starting and braking forces from the trains. I have shown this picture in a separate page so that you see the TPG span from the closer view. So as I said, first the loads from the train are applied on the ties, then it will go to the stringers directly, then it will be transferred to the floor beams, and then it will go to the girders, and from the girders it will go to the bearings and then the earth. This is the example of the TPG span in actual. This is another example from the side view. This one is the underneath of the beam spans. As I said, the beam spans consist of so many beams right next to each other. They're shallower, and each of these beams take some portion of the loads that is applied on the overall bridge. This is another picture of the beam span. Similar to what I said for girders, the same thing happens to the beam spans. Since bending moment is usually maximum near midspan, the role of these components are most important at the midspan location. And by these components, I mean the top and bottom flanges. And the web is more important in the support parts, because in the support we get the maximum shear. This is also another picture from the underside of beam spans. I will go to the trusses next. So in the through truss members, the primary components are stringers, floor beams, and trusses. The hangers do not exist in the deck truss. They only exist in through truss members. We also have some type of component called posts. This is what is called end post, and the post, and also this is what is called hanger. We also have diagonal members in the trusses, and we have also end panel members. The end panel members are two kind of end panel configurations. The function of each component in the panel, including the diagonal, depend on the way they end in diagonal, in the way the end diagonal is connected. If the end diagonal is connected U1, U0, this is U0 to U1, they function as tensile bottom chord members. If the end diagonal connect L0 to U1, they're like compressive end post members. This is also another example of through truss from the side view. The top and bottom chord on the through truss behave exact same as the flanges in the TPG. This is another example of the through truss from the side view, and the top chord behaves same as the top flange in the TPG. The bottom chord behaves same as the bottom flange in the TPG. This picture shows the example of the deck truss. As I said, in the deck truss, the whole truss behaves like the deck and the train goes over the deck. This picture shows the example of the deck truss in actual. This one shows it from the top view, the deck truss from the top view, and this picture shows the deck truss from the inside. And as you see, we have bracings here, lateral bracing. We have the vertical members, diagonal members here. These are also some of our bracings here, as you see. Here, we are comparing the trusses and the TPGs with each other. As I said, top chord in the truss is same as the top flange in the girders. Bottom chord in the trusses is same as the bottom flanges in the trusses. Vertical and diagonal members in the truss behave same as the web in the trusses. Trusses are essentially analogous to deep efficient girders. They are used in place of girders for span length over 125 feet because the material required to stiffen the deep web makes girder uneconomical. In a truss, the top chords perform the role of resisting the bending moment, similar to that of the top flange in a girder. Similarly, the bottom chords of a truss perform the same function as the bottom flange of a girder. The function of the girder web, which is to resist vertical shear stresses, is similarly performed in a truss by the vertical and diagonal members. This is the example of the steel arches. This is another example of steel arches. This one also shows it from the bottom view. The next one I'm going to discuss are the timber bridges. As you see, timber bridges are sitting on timber piles, and these are the pile caps, and these ones are the pile cross bracings. And as you see, the rails are placed on top of the bridge, and the train goes over the bridge. This is the example of timber bridge in actual from the side view. This is the cross section of the timber. As you see, it consists of two steel rail, cresset, ballast here. These are what are called planks. These are what are called piles. This is the timber cap, and whatever goes into the ground is considered as piles. This is another example of timber bridges. This one also, This is another example. This is actually one of the largest CN mixed bridges. As you see, this one is the timber bridge. These ones are the truss bridges here. And you see it's a long span with various span types here. Another type of spans that we have are the reinforced and pretension concrete spans. Concrete permits casting in various shape and size and has provided the bridge designer with a variety of construction methods. Concrete members are used to carry axial as well as bending type loads. Since concrete is weak in tension, members are reinforced with either mild steel or high strength steel to resist the tensile stresses. In this figure, you see different concrete cross sections. The right one is the rectangular beam. This is the slab type. This is the T-beam, channel beams, and these are actually the most common shapes used in the in the design and analysis. This one is I-beam, box girder beam, and voided slabs. This figure shows the concrete superstructure types. In the next slide, I'm showing you some examples of the concrete. It's good to know that sometimes delamination happens in concrete structures. Delamination occurs when a layer of concrete separates from bridge deck or beams at or near the level of the outcome layer of reinforcing. A delaminated area gives off a hollow sound when struck with a hammer. When the delaminated layer of concrete is removed from the member, the resulting hole is called a spal. In other words, spal is a roughly circular or overlapped depression in the concrete. Spals are formed by the separation and removal of the portions of the surface concrete, revealing a fracture roughly parallel to the surface. Reinforcing steel is often exposed. The common shallow porthole is considered a spal. In the next slide, you will see another example of the reinforced concrete span. Some of the causes of concrete deterioration can be explained as temperature changes, which has the expansion and contraction. Freezing and thawing is another reason. Chemical attack, surface component in soil and water, moisture absorption, shrinkage forces, elongation of reinforcements, corrosion of reinforcements, foundation movements, overloading, impact or collisions, and so on. So these are what puts the concrete spans in danger. In this slide, you will see the pretension avoided concrete box girders. This is also another example of the CN railway bridges. This one is actually the steel railway bridge that you see. I'm going to show you different spans right now that CN has. This is also another long span that we have at CN with long bends. So if the support of the bridges are made of steel, that's when we call them bends. This is another bridge that has two usage. The bottom part is the highway bridge. The top part is the railway bridge. This is an example of our movable bridges. As you see in this picture, whenever the ships want to pass, this bridge goes up, and whenever the trains wants to pass, this bridge goes down and the trains goes over this bridge from here. This is also the construction video. Let me show you the next one. This video shows the construction site and how people work while the bridge is replaced, or the new bridge is replaced with the old one. So I'm just gonna wait so that you can see this video fully. And you see how many people work on the bridge site, while it's not only a couple of people, it's so many people that each of them have to handle a specific job at a site. Some of them work on the bridge directly, some of them do the side jobs. As you see, they are now replacing the bridge. They're bringing the new span to be replaced. Here, this is the through truss span. And they are replacing this one with the old one. And as I said, the through truss is the truss bridge that the train goes in the middle of the bridge. If it goes over the bridge, on top of the bridge, it's the deck truss. But once it goes in the middle, it is the through truss. And as I also said, the top chords behave same as the top flanges in TPG. The bottom chords behave as the bottom flanges in TPG. This is what is called end post. And these are our diagonals. These are our vertical members. And having each of them is very significant in the bridge because each of them can handle a specific loads that is applied on the bridge. Yeah, and that's how they have replaced the new span with the old span. This is also the example of our movable bridges. This picture shows the open and ballast deck. As you see here, when we say open deck, it means that we don't have any ballast over the bridge. So this is the example of the open deck. But once you put the ballast on the bridge, you see these are ballasts. We call it ballast deck, and usually the thickness of the ballast is around 18 inches. This is the in-service. This figure shows the in-service maintenance of the bridges. The truck goes over the bridge and inspects the bridge and let us know what we need to consider in our analysis and rating of the bridges. For the bridge inspection program, that's actually what mostly the bridge quality group does at CN. Every year, 5,200 bridge inspections should be performed annually. 3,100 culvert inspections must be done. For tunnel inspection, 300 bridge substructure scarce studies, and approximately 50 underwater diving investigations should be done annually at CN. This is the example of our scar tracking. I'm not getting deep into it because I mostly want to focus on the bridges and structure parts. This is also shows the slide about our underwater inspection because some of our bridge substructures are underwater, and those substructures also needs to be inspected. As a matter of fact, we hire some contractors and they dive into the water and they try to inspect those substructures that are hidden in the water. And it's a really time-consuming and costly procedure for all the companies that have some substructure under the water. This table here shows the condition ranking table, which we use daily at CN. Number 1, as you see, it's in red, so it shows that the bridge is not in a good condition, and number 9 means it is in excellent condition. N and X, each of them means not accessible or not applicable. Whenever the bridge inspector goes to the bridge, they have to use these numbers to show what kind of condition the bridge is in. As you see, this is the bridge inspection form. And as you see here, these are, once an inspector goes to the bridge, each inspector needs to fill this form for each of the bridges that they are inspecting. And those numbers, the ranking numbers that I showed you in previous slides, are the ones that are used here. And simply when you put 1 here, it means that the bridge is in a really good condition, and you don't, in a worse condition, and you don't need to, you have to do a very hard inspection on that and do multiple analysis to make sure whether the bridge is safe or not. And this is also the substructure form. For each of the superstructure, substructure, and spans, we have different forms that need to be filled, and after that, these forms are given directly to the rating group to do the analysis and rating of those bridges, and if the bridge needs to be replaced or repaired, then that's when those information goes to the design group. For the structural cracks, we have two different types of cracks: structural cracks and non-structural cracks. The structural cracks affect the load carrying capacity. They're caused by failure of the material. They can result from poor handling, overloading, or being stuck. And non-structural cracks are those ones who do not affect load carrying capacity. They have minor problem and they have only appearance concern. In this figure, you see that if that crack happens in the middle, they are considered as flexural cracks, and if they happen at the support, they are considered as shear cracks. A crack is a linear fraction in concrete. There are two basic types of cracks, as we said, structural and non-structural cracks. The structural cracks have the potential to be a serious problem because they can affect the structural capacity of the member. Structural cracks are typically caused by dead load and live load forces. They can also be caused by stresses in members whose expansion or contraction is resisted, such as by frozen bearings or by forces due to the expansion of a slab of back wall. There are two types of structural cracks. Fractural cracks, as you see in this figure on the top one, starts in the maximum tension zone or the maximum moment region and proceed towards the compression zone. And shear cracks, which are the diagonal cracks that usually occur in the web of the member near the support. For the non-structural cracks, we can say that they are a minor problem themselves and do not affect the load carrying capacity of the member. They can, however, provide openings for water and contaminations, which can lead to serious problems. There are two types of non-structural cracks: temperature cracks and shrinkage cracks. Damage is dependent on the temperature attained and the duration. Generally, concrete perform well after exposure to fire. Efforts that apply could water to heated concrete may cause swelling, cracking, and the enrichment of steel in the concrete. Sorry, someone is talking. Are you asking questions?
Pocket deal. Don't worry. Go ahead.
Okay. Also, we can talk about concrete defects, the movement, foundation settlement, scar, and erosion, slope failure, impacts, or even the relocation of tracks on the structure, plant growth, chemical attack, marine bores. These are the concrete defects that can happen. Also, we can talk about masonry defects, which are similar physical and mechanical properties as concrete. They are susceptible to many of the same kind of deterioration. Their inspection is similar to the concrete, and they look for deteriorated or missing stones or bricks. This one is also the video of time lapse that shows you how to take one old and unapplicable span out and replace it with the new span. So basically, you have to block the whole bridge so that no train goes over the bridge. And usually that's really hard because that's how the company is making money, by moving the trains. So whenever you replace the span, you need to do it as soon as possible. So all the work should be done simultaneously to avoid any time missing. This figure shows an example of poor construction detailing. This figure is also showing the pumping column. This is also another defect that can happen in the bridge. This shows the web fracture. This has been the web fracture that has been repaired in the field. This is the drilling a hole into the member. This figure shows the fracture of vertical gusset plate. So I'm showing you different things that can happen while the bridge is on the site. And this one shows the unconnected tension-only braces. This figure shows the vehicular impact, as you see here. Crack propagation. This one shows our 6 beams here, and as you see, this beam here is a little bit to the right side. Each component of a bridge, depending on the type of the span, is designed to perform a specific function, and if it fails to perform so, then when the failure or other stuff might happen to that component. In this slide, you will see how the lateral bracing is damaged. So this bracing is the only one which is working right now, and this one must be kept in good condition to avoid inducing additional stresses in the girders. And once the company gets time, they have to replace or repair this one as soon as possible. In this figure, you will see the secondary bracing members. This one also, as you see, is damaged and needs to be replaced, repaired, or strengthened. In this video, I'm showing the crash beams on low clearance bridges. When the bridge is low and different trucks are trying to pass over the bridge, and they attack the bridge and the bridge gets damaged. So let's watch this video together. So it's really important to have the good estimation of the height of the bridge that we want to build, because once you build a bridge, it's really hard to take it out and make it, higher. This type of video that you saw happens many times. We have so many emergency situations that they call us and they ask us to go to the office because there was a bridge hit by a truck or some other companies, and they are when mostly the insurance company are also involved, because both the bridge and the truck are hit, and the insurance needs to cover for those damages. In this figure, you will see the barge impact, direct hit of bottom lattice cord. The next figure shows the barge impact in elastic bracing buckling. This one shows also barge impact, connection rupture. This is another example of damage that can happen on the bridge, which is fire. This one is also fire. This type of fire mostly affect the timber bridges because they are the ones most vulnerable to fires. This is the fire on steel bridges. As you see, the ties, which are made of timber, are the ones that are heated mostly, but the steel structure are also affected by fires. For sure, not as much as the timber bridges, but still the steel structures can be hit by fire. As you see in this picture, this is the example of the fire on steel bridges, and you see how it has defected our steel members. This figure shows the high wind derailments. When the wind came, then you see that the train has fallen down from the track. So when the wind is so high, there is a possibility that the train falls down the bridge. This is also another picture of high wind derailment. This one also, you see how the bridge has been hit. when the train has fallen over the track. This is another example of the bridge heat, which is flooding when the water comes up. This is also flooding. This one is the washout. This is another example of washout. I'm showing you different examples of what might happen to different bridges and what we challenge daily at company to be able to protect our bridges and give service to all around our branches in US and Canada perfectly. This is our concrete arc washout. This is another example of concrete arch washout. This is another example, as you see. This is scarring, rock slide. This is also rock slide. So these were all the defects and damages that could have happened to bridges. We must be careful about those. We must have a plan for those, because sometimes once they happen, they put us in emergency situation, because there are so many trains scheduled to go over those bridges, and once something happened to that bridge, we have to stop those trains. And the best thing we can do is to find a solution to go over that problem and make that bridge effective and applicable again, so that the train can go over that bridge as soon as possible and avoid any confusion or any delay in our train schedules. This was it for me. It was a fun presentation for me. It was nice to be with you guys, and I really appreciate the time you put into listening to this presentation. And if you have any questions, I would be more than happy to answer those.
Thank you, Dr. Khademi. Now I want to open the space for everyone listening. If there are any questions, please just raise your hand and I'll take care of you. So first person is Javier, so please go ahead.
Hi, very nice presentation. Thank you very much.
Thank you.
I have one question that may be two. I want to know how much concrete bridges we can find on United States or CN constructions versus steel bridges. And the second part of my question is how often you find damage on these two different bridges or kind of bridges, still on concrete. So you can maybe help me to see which construction method is better for this kind of situations like trains.
Thanks for the question. That's actually a very good question. We have so many steel and concrete bridges all around US and Canada, and it depends on the usage of that bridge. Usually for longer spans, we use the steel bridges because it's easier to have the longer spans in steel. The maintenance, the construction, everything is much easier. For shorter spans, we try to use concrete bridges. For both of them, depending on the situation, depending on the weather, on the temperature, on the condition, where that bridge has been built, for both of them, we face different challenges. As I told you, for example, your question was mostly about concrete and steel bridges, but as I told you, for timber bridges, the main damage that can happen to timber is fire. So whenever you build a timber bridge, you have to make sure you build it in the places that they have the less chance of getting into the fire. Same thing happens to concrete and steel bridges. For the steel, you know that it is susceptible to corrosion. So whenever there is lots of rain or lots of snow, that's when these type of situations comes into account. So you have to either avoid building the steel bridges in those type of area or have some kind of protection plans for them. For example, dyeing or coloring or putting some type of specific material on steel so that you can avoid those type of corrosions. And in response to that questions that you ask, how often you go over those bridges, we do it as much as possible. So we have an inspection group specifically that they go every single day to those bridges and they inspect those bridges and give us the report of those bridges. And then in our team, we analyze those bridges. Even me and my coworkers as a bridge rating engineers, we also sometimes when we have time, we go to bridges and we try to inspect some of the bridges around us whenever we have time to make sure that those inspections were performed correctly. And if the bridge is in danger, for sure, that would be the priority to do the analysis. And if it's just some basic corrosions that has happened, we just put it in order. And whenever it's their turn, then we start analyzing those bridges. But if we see that there is an emergency situation or this bridge needs the maintenance as soon as possible, or we might put people or customers or the trains in danger if we don't analyze or don't replace this bridge, that's when the emergency situation comes into account.
All right, thank you, Dr. Khademi. Khademi, I'm sorry, is there any other question? I have myself some questions. I really hope not to bother you too much.
No, it's okay, go ahead, Federico.
But first, I want to know, do we have any question on the web, on the online? Apparently not. Well, if maybe they're a little bit shy. In the meantime, I'm going to go ahead and allow myself to ask a couple of questions.
Sure.
The first one is I am very interested how the HDPG type of bridge controls a lateral torsional buckling. For me, it's still, I don't get it yet, quite yet. How do those bridges control the compression cord?
So are you asking about truss bridges or TPG spans or in general?
No, just the HDPG. I mean, I understand how the deep plate girder work when you go from a boat, but when you're connecting yourself lower, when you're going, when you connect yourself to the web.
Yeah, you're right. Yeah, that's actually
you cannot
really
just
good
put
question.
any bracing member, or else the bridge won't work. I mean, the train has to pass anyways. So how do you control compression?
Yeah. So the thing is that most of the time we try to have even TPG or DPG. We usually avoid having the HDPG or HTPG spans. But whenever we have those type of spans, what they do is that they try to make those cross sections stronger and have some secondary members that can be used to strengthen the bridge and have it and make it more applicable. And sometimes when you compare that HTPGs with the actual TPG, you see that it has the more powerful cross sections and also more strengthening members in that compared to the actual TPG.
Thank you very much.
Those spans are shorter.
Yeah. I can see that. Yeah. They're not that long. That's still. I was killing my head how to understand that a little bit. Okay. Yeah. I'm going to see if are there any questions online, or I'll continue because I'm crossing down my list right here. This is an opportunity for us to learn. Dr. Khademi, when you go on field and you are doing your visual inspections, what tools do you take like a must-have? I mean, you're going on field and you're going to inspect of these bridges. What are the tools you most often take on the field to do the job?
What I can tell you is that always remember this: safety, and safety. That's the most important thing when you go to the bridge. So the first thing that you have to have when you go to the field is the life critical tools that you have to have with you. The first one is the helmet that you have to have over your head. If you go to the bridge, you have to have the life-saving vest, so that if the train comes, or if something happens, or if you fall into the water doesn't take you with it and someone can take you out of that water. The other things is that you have to have a special boots. So it's not the normal boots that you can buy from any store. It's the specific boot that even if you go on the pin doesn't go into your foot. So they are mostly very heavy. They are very large. So your foot usually is shown larger than it sounds, it is in actual life. The other things is that you have to have safety glasses to avoid something going into your eyes. You have to have the gloves. Most of the times you have to have the colored vest. Mostly it is in orange or in yellow so that people know you are working over there. And also you cannot just walk over the bridge and do the inspection or the visualization. You need to contact the specific departments by your company and let them know that I'm going on this bridge, and let me know what are the train schedules, and if the train are coming right now, my work is emergency. Just stop those trains. My work is taking 15, 20 minutes or 8 hours or whatever time you need to go over that bridge. And they're gonna stop those trains from going over that bridge. So the thing is that you cannot just go there without having it scheduled. And that's very important. And I can tell you, even if there are so many plans ahead of going to the bridge, and even if there are the company has stopped those trains or they have told them not to come, sometimes still something might happen to the employees, and that's when you have to be careful. You have to have other than yourself, most of the time you have to have someone by you so that they also watch you when you are on the bridge. So whenever we go for testing, for visualization, or for inspection on the bridge, I'm not going by myself. I'm taking some of my coworkers with me, and we are watching each other once one of us in on the bridge, because anything can happen. Someone might have made a mistake, because we are people do mistakes. And although there are so many plans ahead of it, when people go to the bridge, there is still the chance of having the error. And that's why you have to take all these things into consideration when you go to the bridge.
Absolutely, absolutely. Safety first. Now, what do you need to become an inspector on the field? Is there any previous preparation? Do you have like a set of qualifications or degrees that you need to have prior to become an inspector for CN, or can anybody just go there, of course, working for CN and receiving the proper technical preparation, or how does it work?
So it's always good to have some kind of experience, or even having the engineering degree, although there are some of our inspectors who don't have those engineering degrees. But what we do at CN is that we have the bridge inspection workshops, and I am one of the instructors of those workshops. So we have those workshops for like a week, and we try to go over all the required theoretical concepts that they need to know, from the bridge types, maintenance, or how those loads are applied to the bridge. So we have a complete package of 1 week workshop for them to go over what we need from them and teach them and prepare them before they go to the field.
Understood. Okay, excellent. And one last question, if we're still on schedule, are you still on time? Do we have still some minutes with you?
Yeah, sure. Go ahead.
Okay, thank you. There in CN, do you have any structural monitoring currently on any of those bridges? And what needs to happen for CN to consider structural monitoring any of those structures that you showed us?
So for the emergency situations, CN does whatever they can to protect the bridges, but whenever they have extra budget amount, they also use those to protect their bridges. So If we see we have this type of budget this year and we can use it for structural monitoring, why not? We are going to use it to protect our bridges.
Okay, and the second part of the question might wanted to ask you, when do you consider a bridge is not so damaged enough to do monitoring and instead do the replacement, as the example that you showed us in that steel truss that you just said, okay, that bridge is absolutely aging, it's completely flooded with fatigue. We don't want to remove it. We don't want to keep it. We don't want to maintain it. We don't want to do any monitoring. We just want to replace it.
Yeah.
Do you have any means, like those rating documents that you showed us, or who does take the decision to say, okay, that bridge is just too damaged enough to maintain it and just keep it on service, we're just going to remove it? When that happens?
So the thing is that first, those type of information comes to the bridge assessment group, which is our group. We try to analyze and rate those bridges, and we will propose some strengthening for those members if we see those strengthenings are applicable. But if you see the whole member is deteriorated, and the whole member, for example, the web of the whole member, the flange of the whole member needs to be replaced, and you see that strengthening those members is not effective, or it's even more costly than replacing it, then we are gonna transfer it to the design group and ask them to design a new bridge and give us the new dimensions for that new bridge. So it depends on cost and whether that bridge is still applicable to be strengthened or not, because sometimes they are too deteriorated to be able to strengthen them.
Okay, that's right. Yeah, when you don't feel like there's it's like what's happening with currently in COVID in countries like us. I mean, they need to see how bad the patient is, and they need to take a decision, unfortunately, but I understand. Well, are there any questions with the people that are online with us right now, or if there are not, I want to thank you for your time with us this morning, Dr. Khademi. Those pictures are amazing. Actually, we just had until like early 11 the professor that takes care of the bridge for the undergrad at the university where I work at, and he explicitly asked me for the video because it contains a lot of pictures with damage that we don't experience here in Colombia because we don't have that type of massive damage. But he wants a copy of the video, so I will make it. I share with him. It's going to be part of the tools that we use for the undergrad students. And I also want to thank everyone that was with us this morning. This is the 23rd International Seminar Series at the Master's Program in Javeriana University. Thank you very much. Thank you, Dr. Khademi. Have a good day.
Yeah, thank you very much. It was a pleasure to have me here.
Thank you, and bye-bye. Have a good day, everyone.
Bye.